down his title.
Oh.
So he will speak about variational formulations of the Fokker-Planck equations, theory, and applications to stability.
Okay. So thanks a lot for the invitation. I came a few times to South America. It's my second time in Rio, and I'm always very happy to be here in any country in South America. I'm always very charmed by these places. So thanks a lot for the invitation, and thanks for coming. I see at least a couple of people here who know these subjects much better than I do, so I hope at least it can be useful for some of you. Actually, I was asked to show a bit of techniques more than results on how to use somehow variational convergence, gamma convergence, and this kind of things. So I thought of a quite simple example in which one can make like more or less, I don't know if explicit computation, let's say, and really compute this sort of limits and so on. So I would just like to take a kind of base example and show to you like what to do in this, with this kind of machineries and tools. And then in reality, the field of applications of the techniques is much wider, and indeed there is not a well-defined field. So you can always change a bit the models, modify things, and so on. And so it's just, I want just to show you these kind of ideas and show how to prove some result. And actually, I think it's quite simple to explain. At least I think we will prove something a bit more general, but just to get an idea of the problem. Many of you certainly have looked at what's a gradient flow of a function v. Like if you are on RD, or maybe you are on your favorite manifold, you have a smooth function v on this space. Yes, like so v will be a smooth function of maybe a manifold M or your favorite or RD. And you look at the dynamics, x dot is minus the gradient of v in x. This is clear to everybody, this notation, I guess. As simple, the idea is that if v has this form, you start here, this is like v of x, yes? And I start in this point. The gradient always points in the direction, minus the gradient, the direction where v decreases the fastest. So this will, when t goes to infinity, the solution will converge to a local minimizer of v. These discretizations of these dynamics are nowadays very widely used to basically to train basically every neural network existing. In reality, there are many variations, like today's best practice is considered this Adam algorithm, for instance, where you kind of follow the gradients along some variables and then some others. So there are, say, several different discretizations of these dynamics. But more or less, this is the idea. Everybody say, okay, but the idea is if you want to minimize v, for instance, you will try to follow some things. It's clear to everybody that in this way, you are not converging to the global minimizer. And indeed, like if you like a bit of stochastic dynamics, what you have to do is like to add a small noise, wait a lot of time, and then reduce the noise to zero. But now, more and more often in applications, they usually just simulate a deterministic gradient because how much you typically, experimentally, people notice that in many problems, like for instance, very large neural networks, it's kind of the price you pay not to really minimize b, but to find sort of a wrong minimizer is still it's worth with respect to how much computational power you save. Just to say, but still, when you optimize, well, even if you follow these dynamics, and you make a discretization, there is you will always make a small mistake, right? Because there is, for instance, machine error due to the minimization step, but also to the machine error, like the machine precision error. Okay, so you can take your favorite. I don't know, in Python, you take the double precision variable as you want. You say, give me square root of 3, make it square, subtract 3. You will not find 3. You will find some error, usually like 10 to the minus 15, typically, something like this, if you do such a simple operation. There is a rather well-known paper by Lee and others in 2019, I think, where it says, okay, what does the discretization is? Since you make mistakes, there is usually a parameter which is usually called eta in this context, which is called the learning rate, but it's just a time step. You know, modern networks, they really like to give different names to very classical objects. So the discretization is the time mesh is the learning rate. But it tells you, no, what you get is not really x dot minus, what you are simulating is not x dot is minus the gradient of v, is minus the gradient of v plus this small parameter eta. Here I think you get the gradient of v square with the plus, I think, plus a small noise, which is square root of eta some sigma v of x w dot. I'm just, maybe, so let's say that, introduction. Yes, I'm not discussing any math. So, one introduction. Yes, okay. So is it clear? You are, in reality, due to the error, sometimes you will make some error in excess, sometimes a defect. So there is some randomness, which is clearly sort of Gaussian, and there is actually a gradient of the positive drift. So what we are thinking is that instead of your original nice v, you have a slightly perturbed. This is the gradient of the gradient. Yeah, it's much less regular somehow. You have a the white guy is v, the pink guy is v plus eta gradient v square. Okay, I should have made some positive perturbation. Sorry. Is it clear? And then you have some diffuse, some stochastic additional term here. So when eta is small, I think that the question is this error that I'm making relevant or not? When I send eta to 0, will I converge to my original dynamics or not? Right? Because if I'm not converging to my original dynamics, then I'm simulating something else. Actually, what can happen is that this slows the convergence to the minimum, really stacks it at some earlier point. Okay? Is it clear that when I add this little perturbation, it could happen, depending on how big is the noise and how big is this perturbation, that when I send eta to 0, I still converge to my original dynamics, my original gradient, or maybe I modified it. Nobody tells me that the solution x eta converges to the solution x with eta equals 0 when eta goes to 0. Continuity of the solution in eta. Yeah, I can wonder about this happens or not. I think it's quite easy to to figure out that this conversion will happen or not, depending on the relative size and also smoothness of the perturbation with respect to the noise. Let's make the two extreme situations. The first situation, there is no noise. Okay? So if I consider x dot equal to minus the gradient of v of x plus a small perturbation, eta the gradient of some u. Okay? Well, in x always. If u goes to 0 in C1, then the gradient goes to 0, and it's very easy to prove that you just converge, even without noise. This is the case where v was like this, and I add a perturbation where not just the perturbation goes to 0, but also its derivative, right? So, so the derivative of the perturbation goes to 0, and I'm still able to just converge to this point. But for instance, if suppose that instead I look at the same problem, maybe I should have started with this, and the u, for instance, goes to 0 uniformly, but not its derivative. Okay, so for instance, u, so v plus eta u has this form. Some small bumps. So for instance, u is, let's call it maybe. So maybe let's think that u depends on eta, which is actually the case that we can more carefully look at. Suppose that u eta. So the perturbation, yeah, otherwise I should have taken it non-smooth, which is also what one can consider. So suppose that u eta of x is, for instance, I don't know, the sinus of x over eta. then the eta, the gradient of the sinus over eta is not going to 0, right? Because there is some 1 over eta that cancels out. And indeed, when I consider the gradient flow of this perturbed potential, no matter how small eta is, then I take it to 0. Since the derivative is not small, I will always converge when t goes to infinity to a minimizer of the pink picture, of the pink function. And so I will always, when t goes to infinity, I will converge here, no matter how smaller I take this picture. So it's clear that I don't converge for every time. Is it clear? A small perturbation, either because u is not smooth or because it depends on eta, but the derivative is not converging, can block my gradient flow. Okay? So I think, so for instance, if I consider, let's say, okay, and that's the question. It's clear that if I add a little bit of noise, this helps me. Because there is some probability that I can overcome this little bump and finally really converge, okay? So I want to look at sort of this kind of problem, x dot minus the gradient theta of x plus, say, the square root of eta. I will soon call eta some beta because like 1 over beta because it's this learning rate I don't like much, but like you can think, you can tell me that v eta, so the question is v eta converges to v, okay? Maybe in some space which can be more or less regular. I don't know, for instance, some w alpha p, who knows what is a w alpha p? Like you have alpha derivatives in LP, something like this, okay, in some Sobolev space. But or you can think we can think in C alpha, for instance, in C alpha. And okay, how far, depending on alpha, how small should be the C alpha norm of eta minus v when eta goes to 0, so that the noise is able not to be trapped in these small bumps. Okay, the bigger is, so if alpha is 1, I don't even need the noise. So if alpha is 1, no matter how slowly you converge to 0, this gradient flow perturbed will be stable. Okay, if alpha is at 0, it's clear that you will need a lot of noise. Actually, the noise shouldn't go to 0 in that case to have a convergence. But for alpha between 0 and 1, you can wonder how big should be the perturbation in a C alpha sense, in such the way that the noise is enough to overcome the problem. We will study a bit more general problem, but exactly on this problem in dimension 1, Pierre Mathieu wrote a paper years ago where he considered the symmetric potential in maybe 97. Pierre Mathieu. And where I think he considered as a one-dimensional, it was, I think, x dot is minus x plus 1 over, okay, plus eta to the a. And here there was a potential, so the gradient of b of x. Now, b will only be, b was not smooth for him. Actually, it was basically a Brownian motion in x. Okay, so, but he proved that for almost every realization, plus square root of eta and noise. Okay, so okay, it's true that what is the gradient of a function which is not smooth is not so clear, but since you are in one dimension with symmetric potential, you can give a sort of a explicit representation of the solution, and you try to pass to the limit when eta goes to 0. So what he proved, I think, is that if a, this exponent a, is more than 1/2, you converge to x dot equal to minus x. But if a is less than 1/2, no, so in this case you have convergence. Convergence. In this case, there is no convergence. Okay, so like the bigger is a, the bigger is the smaller is a, the bigger is the perturbation. I'm discussing eta to 0. I look at the limit eta to 0. when eta goes to 0, this stochastic differential equation converge to its formal limit when I put eta to 0 in the equation, the solution does converge to the formal limit or not. It's since there is this effect that this bump can stop you, it could be that you don't converge, okay? And if you converge or not depends on how big is the noise compared to how strongly, so to the size of the perturbation and how regular it is. Okay, so we will try to understand, maybe to include also, here this potential is like C1/2, alpha is 1/2, and I hope it's 1 and 1/2 and not 1 for A, but I think so. So we will try to understand, maybe also to understand the case where A is 1/2, is exactly 1/2, for instance, what happens. Okay, some problem like this. And so what I would like to convince you is not really to study this problem in details, which is in reality is quite simple, and one could do it in many, for instance, with at least in dimension 1 with some explicit representation. But I want to just be considered a bit more general problem and show you how these variational techniques, how powerful they can be in some cases, because we will see that once we put in place a little bit of machinery, technically the proofs will be very simple. Okay. By myself, I used these kind of techniques once, maybe 8 or 10 years ago, to prove something completely unrelated, the convergence of some singular PDE, so nothing stochastic, to some step on this. This PDE came from some statistical mechanics model introduced by Leibowitz, and the limit was some so-called Stepan problem. What impressed me, and that's why I liked these techniques, is that in this case it was not just a way to prove the convergence, but to guess the limit, because it was something where, like, if you look at the PDE, it's not clear what the limit is, and this variational convergence gave you a hint. Without this, just looking at the differential problem, I would not be able to make a guess. Then once you have a guess, maybe one can prove something. So, and okay, so still as a part of the introduction, I would like to tell you where these techniques are from, because indeed they are not from the, these techniques are quite simple. You just write an inequality and pass the limit. But what I want to say is they are not from the probability community, but they come more from analysis and a bit of differential geometry community, even if some of the people are, I think, quite well known also in the probability community, like Otto, Felix Otto, Cédric Villani, since I'm Italian, and also he's a great mathematician, Luigi Ambrosio, and many, many, many others, which I'm probably forgetting. And this approach in which you use gradient flows to characterize things like curvature in metric spaces and so on, it's a very fashionable approach in these days. And in the last 15 years, so since 2010, 2 Fields medals have been awarded for people working on this kind of subject. So it's quite powerful and fashionable also. I learned a bit of these things many years ago when I was sharing an office with my friend Nicola Gigli, who at the time he was quite young, but also has become rather celebrated mathematician, won prizes and so on. And he wrote a book on the subject together with D'Ambrosio and Savary. But okay, off the record, he was the youngest guy, so he really is the guy who wrote the book, made all the exercises and so on. It was a monumental work, and so it's Ambrosio, Gigli, and Savary. It's called gradient flows. I think it's called, I may be wrong with the title, it's gradient flows on metric spaces. Spaces and spaces of probability measures. So if you know, if you like stochastics and you know Bakry-Emery theory, the theory strictly contains Bakry-Emery. The book is like 2005, 7 maybe, around 2007. At the time, it was the absolute state of the art. Now, maybe, I don't know, if you open archive on this subject, every day there are papers. So nobody can write a book on the state of the art anymore. So actually, we will not look at gradient flows because a gradient flow in the context of probability is a reversible process, and not all processes are not all Markov processes are reversible. And there is this famous citation, which is usually wrongly attributed to Ullmann, is that reversible statistical mechanics is like non-elephant biology, right? Like, it's not in biology you don't divide animals in elephant and non-elephant, but somehow the name in statistical mechanics is a bit misleading, that one divides the system in reversible and non-reversible, but reversible is sort of a miracle. It's very rare in practice. So since I had a bit of this background of statistical mechanics, if something is reversible, I always wonder if there is some non-reversible version. So for gradient flows, absolutely there is. But OK, we have this problem. We have this problem. Now, like this curve in RD, or your favorite manifold, for any curve, not for this solution, but for any, let's call it yt, for any sufficiently smooth function of t, OK, I can compute y of xt. This will be y of x naught plus the integral between 0 and t of the differential of y and ys, y dot s. I like to make duality in this way. Yes, it's like dv scalar y dot in ds. The fundamental theorem of calculus, yes? The function at time t is the function at time 0 plus the integral of the differential of v times the derivative of y. Is it clear? Is this not, you prefer that I write gradient? It's OK. I think it's OK. So this is always bigger or equal than minus y v of y naught minus the integral between 0 and t of the norm of dys y dot s in ds. Yeah, just and this is always so bigger or equal. Oh, sorry, this is no minus here. V of y naught minus 1/2 the integral between 0 and t of dv square in ys minus 1/2 the integral between 0 and t of y dot s square. Right. Every yt satisfies these inequalities, that this is bigger than this. Right. That's this is just, I put the modulus inside, just the the scalar product is less than product of the norms, and the ab is less than a square b square, plus a square over 2 plus b square over 2. So when are these, OK, when I'm still in the introduction, I don't want to do much formal math, when is this inequality an equality? Actually, it's a very simple thing. I could have written it differently, but well, the first inequality here, these two vectors are so the scalar product of the two vectors is equal to minus the product of the norms if they are collinear, and also so they are on the same line and point in the same direction. Yes. So this will be equality if y dot is like points in the with the minus in the opposite direction of the gradient of v. So if y dot is minus some, I don't know, alpha, the gradient of v of y. So for almost every s, see, for some alpha positive. Yes. Sorry.
When you wrote, so you write, when you write it as pair, you use t, but when you write it.
Yeah, because that's actually correct. Yes. So because this is the gradient and this is the differential, what can I do? Yeah, right. Here I could, here no, but here I could write gradient if you want. And when is this AB an equality with 1/2 a square plus b square if the size of A is equal to the size of B? So this tells me that alpha is 1. Right? Because these two vectors must have the same size. Okay? So the same norm. So you see that this thing, which is always an inequality, becomes an equality exactly if the curve is a gradient flow. Okay, so I could, instead of defining the solution as, you really make the derivatives and so on, I say, okay, what is the gradient flow of a function v? Of the function v is a curve, so you could define, I will be very quick because, very informal because it's the intro, this is not what I want to do, but classically gradient flow of a function v, say on Rn, I say that x is a gradient flow of v. So this is a function from your favorite manifolds to R. If v of x naught, if the reverse inequality is true. So the reverse inequality is that v of x naught is bigger or equal than v of xt plus 1/2 the integral of the gradient of v, or the differential of v squared of xs ds, plus 1/2 the integral between 0 and t of x dot s squared in ds. Okay, if the opposite inequality is true, I say that x is a gradient flow. If v is a smooth function, these two statements are absolutely equivalent. Okay, what did I earn in this definition? Well, is this useful? Well, actually, yes. First, it's useful because advantages, okay? Advantages of this definition, advantages. First, I can define this inequality also on a metric space, not just on RD. If you, so it's always less or equal. So I say you are the gradient flow if it's bigger or equal. Then it will be equal. Then it will be equal, okay? Well, first, okay, if you it's already an obvious, quite obvious a priori bound. Yeah? You tell me that if v is finite at time 0, it's finite at every next time t for the gradient flow, that the integral of the gradient of v square is finite, that the integral of x dot square is finite. That's already not bad, but the first advantage is that m, I can make this definition works on a metric space. Maybe there is no solution, but as a definition it works. Why? So you know that if on a metric space, so M now is not, I don't know, a manifold where you have a differential structure, you just have a metric structure. What is, for instance, well, what is V? It's clear to everybody. Even if V is a function from the metric space to M, X is a continuous curve, I can always do V of X naught and V of Xt. So these two terms, no problem, right? But then I say that X is X, so a curve from, say, some interval of time 0t to M is absolutely continuous. Absolutely continuous. I'm using already too much time. If there exists a function f in L1 of 0t such that the distance between xt and xs is bounded by the integral between s and t of f of r dr. Okay? So if you are in RD or on a MED, this is exactly what's an absolutely continuous curve. Now there is a simple remark, which I will not prove, but we will not need it either, is that you can define x dot s. If x is absolutely continuous, you can define x dot s as the limit, the lin sup, when t goes to s, of the distance between xt and xs divided by t minus s. Then x dot r is the optimal f for this inequality. Yeah, like if this inequality is true for some f in L1, it's true for this function, and that's the smallest function you can use in the inequality. Okay, so this is called the metric derivative of x, and okay, we have got who we should put here, also in the metric space. Okay, and then now the definition. You will say that the function f from m to r may be union infinity. I'm not really an expert of this thing. I just wanted to make it a part of the introduction. Is an upper gradient for V is a upper gradient of V if V of xt minus V of xs is always smaller or equal than the integral between s and t of f of x star dr for all absolutely continuous curve. Okay, so like for instance, if you are in RD, taking f the modulus of the gradient of V works. Sorry, I forgot the x dot r, of course, dr. Okay, if I take, like in a smooth context, I can take f, the modulus of the gradient of V. Okay, usually, so remark, in many cases, f, also, what's called the modulus of the gradient of V in x, which is just the lim sup when y goes to x. So now, before the distance was up, now the distance is on the denominator, the distance between x and y. So here I should be slightly careful to adapt the definition to infinite dimensional context, but I shouldn't take, I don't know, the modulus of V of x minus V of y, because as you know, very often functions are just semi-continuous on big spaces, not continuous. So when you take the lim sup, it's a little twist, but like in Rn, this will give me exactly the modulus of the gradient of V. Otherwise, I should take the positive part of the variable that doesn't move minus the variable that moves in the limit. So okay, let's say that V admits this as an upper gradient, for instance. Then I don't write it, but definition gradient flow on metric spaces. Like I say, oh, well, what does it mean to solve x dot equal to minus the gradient of V on a metric space? Well, an absolutely continuous curve on the metric space. So is the gradient flow of V if for every time t, V of x naught is bigger or equal than V of xt plus 1/2 the integral of the square of the upper gradient, say that one, plus 1/2 the integral of the square of its metric derivative. Okay, that's it. Okay. Of course, such a definition would be completely not very interesting if one doesn't have relevant examples. And there are relevant examples. There is one which I want to mention. Yeah, I think it's worth to mention, because then we will see basically exactly this example, but maybe with a different notation, but with a similar technique. I apologize. Before the example, so I list second advantages. Yes, advantage number two. Okay, the first one was that I can define it on a very general framework. What is it? So while of course on a metric space I wouldn't know what does it mean grad V. Yeah, there are in descriptive mathematics there is a standard result that you can always embed a metric space in a linear space. So while the modulus of the gradient of a function doesn't depend on the embedding, the actual gradient does. So this has a metric sense, but there is no way you can define the gradient in a metric space. It's a very abstract result, but just to say that, with the inequality, it's clear that these objects have some intrinsic meaning, while x dot minus gradient of V does not. Only this remark. Advantage number two is what I want actually to discuss a bit maybe today, next time, is exactly the stability. Okay? So suppose even in Rn, that xn, you have a curve xn, is the gradient flow of Vn. Everything is nice and smooth, you are in Rd, okay? Okay, if Vn converges to V in C1, we can use the standard techniques to prove that you just write the definition, what does it mean to solve the NOD, and you pass to the limit. If Vn converges to some V in C1. if v n converges to some v in C0, we already have seen that there is no hope that the limit, the gradient flow converges to the gradient flow. So let x be a limit point of xn. So suppose that this curve converges, a limit point of xn. I don't know, in C, for instance, uniformly in time is not important. Okay. So the question is, what do we need? What do we need to say that x is a gradient flow of v? There is no noise. It's more or less the question I was asking at the beginning, just without noise. Yes. So, I tell you. I tell you 3 conditions that will be less than this guy converges in C1, and then we will check that. Okay, first, of course, is a convergence of the initial condition. Yes. So x at time 0, n converges to some x at time 0, and but I want a bit more. I want that the lim sup of the energy of the Vn of the initial condition actually converges, but formally it should be not bigger than v of x0. Then I want a second condition, which is that x0, for every x and for every sequence xn that converges to x, the lim-inf of Vn of xn is bigger or equal than v of x. For instance, if you converge uniformly, as we said, which is not enough for the gradient flow, this is true. So this is very kind of weak condition, okay? This together with the first the condition tells us that the energy of the initial data really converges. And then A3. And now I need something on the gradient, but less than converges in C1. I need that for every x, for every sequence xn that converges to x, the lim-inf of the gradient of v, let me write the square. This will be, you can remove the square, of xn is bigger or equal than the gradient v squared in x. This, and it's absolutely true in infinite dimensional context, is it's less than convergence in C1, but it is much less than convergence in C1. So no matter how you converge to x, the cost, the energy of conversion of the sequence in the limit is more than the energy of the limit. And this is true also for the square of the gradient. Okay? A1, A2, A3, then, maybe I will write it there. I will convince you very quickly that A1, A2, and A3 imply that x is a gradient flow of V. Okay? A1 plus A2 plus A3 imply that x is a gradient flow of V. We have nothing to do. We just write if you try a differential approach, it's very hard to use those conditions to prove the differential approach, like to pass in the limit in the differential equation. But if I write as an inequality, yes, I knew this inequality, xn was a gradient flow of Vn. That's what it means. It means this. Plus 1/2 the integral between 0 and t of x dot n s square in ds. This was the gradient flow, what defines being a gradient flow of Vn. Then I take the lim, the lim sup. So let's say that I say that v of x0 by a1 is bigger or equal than, so this is hypothesis A1, then the lim sup of V of x0n Sorry? Vn. Thanks. So, okay, this lin sup and liminf is just because I should have put myself on the convergence subsequence. Okay, but let's think that. So this will be bigger or equal than the liminf of this sum. Okay, the liminf of the sum is more than the sum of the liminf. So this will be bigger or equal than the liminf of Vn of x and t plus 1/2 the liminf. This liminf are all in n, of the integral between 0 and t of the gradient plus 1/2 the liminf of the integral. So can I pass? So I avoid to write 5 times always the same thing. Now this by A2 is, I say that xn converges since uniformly, or maybe for every t, to its limit x along, I take this limit only along the subsequence that converges, okay? So here I will get bigger or equal, I get the right inequality, because, okay, on the initial data is on the other side of the inequality, so I need smaller or equal, and on the rest I need bigger or equal. Here I will get v of xt. So here I can use Fatou's lemma, pass the limit. This is positive, so I pass the limit inside, and the inequality goes in the right way. So here I get 1/2 the integral between 0 and t of the gradient of v square of xs ds. And this, well, allow me at least on RD or on a manifold, but in reality in general, this is an H1 norm. So norms are lower semi-continuous. If you converge, the limit of the norm is bigger than the norm of the limit. So here we get plus 1/2 the integral between 0 and t of x dot s square in ds. As in our case here, it will be just that you have to change a limit with the sup. So this inequality is also true. So you see that in the violet inequality, we got that x is a gradient flow of v. Is it okay? So I didn't need C1, I need a bit less if we are in Rn. But let me show you an example without proofs, because we will make a bit of a stronger statement where there is a, let me just make a very famous example, just not to mention all this stuff about gradient flow without at least one example. So example, take maybe RD, take RD, or a manifold. And it's good to think that that it's a manifold. I will tell you in a moment why. Let's think it's actually I could think any metric space indeed, and then we consider as a metric space P2 of M, the Wasserstein space of order 2. Should I recall what is it? This is just all the these are Borel probability measures on M, all the probability measures on M, such that the integral of the distance between x and y squared in d mu of x over all the space is finite. So it's just probability with finite second momentum. It's not hard to check due to the triangle inequality that this is finite for some y, if and only if, so it's finite for any other y. Being finite or not doesn't depend on y due to the triangular inequality. This is called the Wasserstein space. So there are probability measure with finite second moment. Okay. Here there is a distance on this space. So distance. Let me denote still d, but this is a distance on P2. I define the d. The square is the infimum of the integral of the distance square between x and y in d gamma of x and y, where the infimum is taken over all gamma such that when you marginalize on the first component, you get mu, and when you marginalize on the second component, you get nu. Is it Is it okay what it means? Like you have product space, here you have distribution mu. You have distribution, here you have mu as a distribution. Here you have nu as a distribution, like, I don't know. Here there is you can think this is an interval. Here is an interval. You can think of the probability as a distribution of mass over these intervals. And gamma, a coupling, is a distribution of mass on this square, okay, on the product space m times m. Oh, I didn't write it, this, sorry. Gamma will be a probability over m times m. Sorry, such that. So gamma is a probability distribution on the product, okay? Things that this distribution are like send. Yes, some distribution of send on this line. So distribution of send on this line. A coupling is a distribution of send on the square, such that when you push down the send vertically, you get mu. And all this send accumulates, and you get, and you push it horizontally, all this send accumulate, and you get the distribution that you have here nu. Okay, that's a coupling between mu and nu. So this is it's not hard to check that this is a distance on this space, and okay, this is start to be useful because we can define. So we fix m. Let's say a probability measured on this space. Okay. So our initial data here for the construction was our space M, a distance over M, and the measure over M, a tripole. That's called a measured metric space. It's a tripole, a non-empty space, a distance over this space, and measure M. I am assuming that this space is quite nice, complete, metric space, separable. There are, okay, the right hypotheses are the main problem in this field. So, okay, I can define then a function h that goes from probability measures on M to 0 infinity. That's called the relative entropy, or the, oh, it has many names, this function. H of mu, this is the supremum over all the functions of f, say, that are in L1 of mu, for instance. So for denotation, is it comfortable if I denote integrals by mu of f means the integral of f in the mu, okay? So what is h of mu? It's, okay, is this, is everybody comfortable with this? What is this object? By Jensen inequality, you always have that mu of phi is less or equal than the log of mu of e to the phi. Now, if I want to change here mu with m, that's not true anymore if I change measure. So the smallest constant I have to add is the relative entropy. You can make this exercise, it's not hard exercise. H of mu is equal to the integral of rho log rho in the m if mu has a density with respect to m. So that's, I mean, radon negative derivative. If I say some words that are not clear, sometimes many things you may probably know, but I give a different name to them. And it's plus infinity otherwise. This integral is well defined because rho log rho is bounded from below. So it's not, I define this way, but it's clear that it's positive because if you take phi equals 0, it's positive. And it's convex in both in jointly mu and m because it's a soup of linear thing or affine functions of mu and concave in m. So it's a standard object. We will see maybe where this comes from. And okay, so I can wonder if there is a gradient flow. If I want to find the gradient flow of this guy with over P2. I have a function on P, in particular on P2, and I can wonder if it has a gradient flow. In the previous sense, it's a metric space. I can define everything. So if there is a curve such that h of mu t, h of mu naught is bigger or equal than h of mu t. Okay, suppose that mu naught has finite entropy plus 1/2 the integral between 0 and t of the gradient of h squared on mu s ds. This function here, many of you have seen. That's actually the Fisher information. And here there is dt mu, so ds mu s So where this means this is a square in this Wasserstein sense, okay? So that's, does it exist or not? It's a bit of a question, but let me tell you one case where it does exist. And that's okay. If M was a Riemannian manifold, for instance, RD, okay, the gradient flow mu t of this entropy, let's say, suppose that M is RD. The M is e to the minus v dx, and say that v, the action of v is bounded from below. And this is a probability, so integral v to the minus v is 1. Then in this case, and the distance is, say, the Euclidean one, then the gradient flow exists, is unique, and is nothing but the law of the stochastic differential equation. X dot is minus the gradient of v of x plus w dot, with x as 0, having distribution mu 0. Is it clear what I mean? Mu t is the law of xt. Sorry, I wrote it a bit quickly. I apologize. So mu t is the solution of the Fokker-Planck equation, is the law at time t of the solution of this differential equation. Is it okay? I don't prove this theorem because we will make something a bit more general, to be honest. But it's checking this on RD or a manifold, Riemannian manifold. It's the first kind of the first paper in this world. I started it all. It's Otto Jordan Kindler Otto, 90 something, 98 probably. I say that the gradient flow of the relative entropy of a Wasserstein space is nothing but the Fokker-Planck equation for a reversible Markov process. Okay, be here there is a square root of 2. What I wanted to say, but actually, this is the interesting part. Actually, this is the interesting part, that you can write conditions. They are called the RC conditions, regularity and curvature conditions, such that if I give you a metric space, you can check this, in line of principle, you can check these conditions on the metric space, namely on the triple MDM, okay? That's the so-called lambda geodesic convexity. You can check some condition on these things, for which it tells you that this gradient flow exists and is unique. Okay? On a manifold, this condition coincides with having the curvature bounded from below, Ricci curvature bounded from below. So you can check in principle this, and then you build some Markov process. So I don't know, you can build, for instance, if these conditions are true, you can build a Brownian motion, for instance, on this measured metric space. Okay, so it's okay. We will always live in a differential context where, like on a manifold, but like what I want to say is that you could do this kind of theories. So I give you, this was just an introduction. I give you maybe 2 exercises that you can try to do, because usually, of course, here you could do, like sometimes people do P and Q with 1 plus P plus 1 over Q equal to 1. So you can do on RD, on RD. I prove, we will introduce some inequality. The Fokker-Planck is like this inequality. What I will not prove is that Fisher is the gradient flow, is the upper gradient of the entropy. It's not hard, but you need to, but we don't care about this statement, because in reality it's not the type of structure that I use. I will make everything quadratic and no interaction, I would say. Everything is linear. I will make everything in the linear case. Maybe last day we can make some simple interaction if there is something. But okay, the exercise 1. Let's make this. Okay, let's make 2 exercises. The first exercise is the following. Suppose that instead of a gradient flow, you have a gradient of v plus r of x and a vector field r, which is not a gradient of v, such that r of x, scalar, gradient of v of x is 0 for every x. You know that if you give me a vector field here, let's call the whole vector field B, you can classify in how many ways you can write B as minus the gradient plus R in such a way that they are this scalar product is 0. Of course, you can always take R equal B and V equal 0, but in general, there are many. You can really fully characterize in how many ways you can do it. Okay? But suppose that we have this structure. Not the gradient of V, but the gradient of V plus a perturbation, which is, however, is a pointwise orthogonal to the gradient of V. Try to write it as an inequality. So the inequality will be V of x naught bigger or equal than V of xt plus 1/2 the integral between 0 and d of gradient of y square of xs ds plus, and you try to find out what should be here. Okay. So for instance, if r is 0, here is x dot square. And exercise 2, I think it's more interesting. So instead of 1/2 square, 1/2 square, suppose that we have a Lagrangian L of x and v. We have two functions, L of x and v, and h of x and p. Okay. They are function that depends on x and the tangent vector in x, like functions of x and rd, x and rd. Okay, and they are one is the Legendre transform of the other. So L of x and v is the sup of a p of vp minus h of x and p, and h of x and p is the sup over v of vp minus L of x and v. Okay, if they are convex, one of the two is, so this just means that they are convex, and the one is the Legendre transform of the other. And they are smooth, take all the hypotheses you like. And then the question is, of the exercise 2, exercise 2 is the inequality v of x naught bigger or equal than v of xt plus 1/2 the integral between 0 and t of L of xs x dot s ds. No, without the 1/2, sorry, plus the integral between 0 and t of h of xs. I think to make it equivalent to what I wrote before, here I should write dv minus dv of xs. Okay, you just should change what is p or minus p in ds. Is equivalent to which ODE. So it's like this is x. This is equivalent to x dot equal to b of x, but who is b? Okay, that's exercise 2. For example, yes, if L of x and v is v square over 2, h of x and p is p square over 2, then b was minus the gradient of v. Okay. But in reality, this being gradient is not so relevant in here. And okay, I think we have maybe 0 minutes left. But maybe I can just ask you a question. So, okay, we will start next time to some preliminaries, and then maybe in the third lectures we will show some result. Preliminaries. So I want to look. I would like to. So I want to look, say, on RD to the equation x dot is like b of x plus, say, sigma of x w dot. But I don't want to use at all this notation. I was just to think that, let's say, b tilde. I want really to use a geometric notation. So I want to think that like sigma cross is some inverse Riemannian metric, or maybe even degenerate, pseudo-Riemannian, if you so, it could be degenerate, but okay. How to say? Is everybody comfortable with this, right? What this means? Yes? Yes, okay. But, okay, then you know that I can think that this is a Brownian motion in this metric, somehow. And these two, so let's say that I want to write like this object, maybe like on a manifold or with respect to a Brownian motion with some given metric. What I means is just that I have an operator, linear operator, the generator of this process, which acts on smooth functions. And this is, okay, I will put some b square root of 2. This is the Laplacian of f in x plus b of x df of x. Right? This is like, it's a sort of Ito formula, right? But, so if I have a metric, this will be the Laplacian with respect to this metric. You can always write this equation locally in coordinates in this way. Just, you know that the Laplacian of f in coordinates has a bit of an ugly writing. It's like the determinant of the square root of the determinant of a, di, aij djf divided by the square root of the determinant of a. So this makes sense also if a is actually degenerate. But so how to say? If you want to write it in this way, there is not di, there is not aij dijf. There is a relation between b tilde and b, which is like square root of a di of aij square root of a, right? Is it clear what I mean? So I prefer to write in this way than in this way, because otherwise I always should subtract to b some derivatives of a and so on and so forth. So it's much more comfortable to write in this way, if I want. But I have nothing against that. You think that sigma is 1, we are on RD, or maybe a flat torus, and when I write differential, it's a gradient, it's always the same thing. It's totally fine, okay? So who else knows what is a one form? Who doesn't know? Okay, okay. It's just a vector field. Okay, cool. But this is a bit, I'm a bit obliged to. It's just a vector field, but I'm a bit obliged for what I write to have a bit of formal writing. So maybe I can take 5 minutes, yes, more, to just be sure that. So I don't pretend to be a. No, it's not true. Recently, I wrote something with some geometry. I had to study a lot of geometry, some algebraic stuff. It's a nightmare. Don't pretend to be an expert in differential geometry. I recently learned what are Jacobi maps. But so, like you have a map which you can think it's a torus, everything is flat, no curvature. I don't care about it. But just as who is on the right, who is on the left. Yes, if you have a curve, a smooth curve here, okay. So I think it's clear that like a tangent vector field in each point is tangent to a different. In each point is in a different space. Like if you have a sphere, right, yeah, a vector tangent here is not a vector tangent here. They live in different spaces, right? So they are all like RD, for instance, in this case. But in general, for us, we will like the space will be a space of probability measures. So tangent plane may also look a bit different in different points. For instance, if the measure is singular. So so like now, if I have a smooth curve, I think it's clear with what is x dot. It's derivative. It's a tangent in the point where the curve is. X dot t is a vector tangent in xt to this space, right? So if I do f of xt, I think that everybody knows that if f of x0 plus, so I write like this, like there is x dot 0, there is t plus small o of t. What is here is a linear function. So you say that the function is differentiable if there is a linear function on the tangent space in x0, right? And this is called the differential of x in x0. Okay, that's who is the differential. So I on each plane, I have a tangent. In each point, I have a tangent plane, and I have a space of functions, linear function on the tangent plane. This is called the cotangent plane in that point. Okay? For us, it will be important, because when this is probability measure, we will have like who is tangent, who is cotangent are really different spaces. Here, it's always RD, right? So, okay. So now a tangent vector field, tangent field is just a section of the tangent bundle. It means that it's a function of x, yeah? That for each x is tangent in x. Like in each point, I give you a tangent vector, right? While a cotangent vector field, this is like in every point, it's still just a vector field. In every point, I just give you an element of RD, right? But I'm thinking that for in each x, I have a linear function on E. Okay? And this I will denote E omega, the duality between E and omega. Okay? This is like how this linear action of omega over E. To recall that is linear, I call it E omega. So this, if there is a notion of smoothness, yes, because the manifold is local is like RD, so to define if it's smooth or not, it's enough to know what smoothness is in RD. And so, it's not completely true. You can make, so it's a smooth manifold. Okay, we have a smooth manifold, so we know what is a smooth function on this manifold. And so one form for me will be just a smooth cotangent vector field. That's what a one form is. Okay. So this D1 is the so D0 is just is the zero form. It's just smooth functions on the manifolds, and D1 is just smooth one forms on the manifold. Okay, and we have a map. It's called the differential from D0 to D1 that associate to a function f. It's differential, which in each x is a cotangent indeed. Okay, and then so then there is actually the dual of this function. We will not use it much, but D0 they are distributions. Yeah, the dual of smooth functions, they're called distributions. Then D1, okay, this is the dual of D1. So linear continuous space, the linear continuous functional on the space of C infinity one forms. These are called one currents. I will just say currents because we will never go beyond one. So this is the space of currents. So what is a current? Is just J is a J of omega. It's the collection of linear function. How to say J? Or J of omega is linear and continuous. How should we imagine currents? Well, a smooth one form is just a vector of smooth functions. A vector field. Local is just vector of smooth function. So a current is just a vector of distributions. It's just a notation for a vector of distribution. Looks very crazy, but it's just that. I think very, very well. So let's make just two examples. If I give you a curve xt, you can make a measure, in the interval 0t. Certainly, you can make, for instance, a measure which is, I don't know, 1 over t maybe, delta of xt, delta over xs ds. I think, is everybody fine with this notation? Is the occupation measure of xs, no? So this measure on a set A is 1 over t, the integral between 0 and t, of 1 if x is in A at time s, ds. So this is like the percentage of time that the curve x spends in the set A. Similarly, I'm sorry with this blackboard management. It's very nice big blackboard. It's really my fault. Similarly, if you give me a smooth curve xt, I can make a current that lives on the curves in the same way. Say jt, for instance, is 1 over t, the integral between 0 and t of delta of xs, x dot s in ds. What does it mean? Like here, jt of to define this current, as you just define it for every one form, right? So this will be, for instance, 1 over t, the integral between 0 and t of x, I always say x dot s, omega of xs, ds. So it's like you have this curve, and this is a current that leaves a transport on the. So sorry, this is nothing but the integral of omega over the curve x 0t. Okay, this doesn't really depend on how you parameterize the curve. Only depends, say, this. Okay, divide by t. It was a bad idea to divide by t, actually. So we will actually, okay, we will not really look at this, but if now x is a random curve, this will be a sorry, if x is a random curve, this will be a random measure, right? If x is a random curve, well, typically you cannot really make x dot, but you can replace this by a Stratonovich integral, or the geometric rough path is also called. Okay, so it will have the okay, let me not divide by t. So this will have the, you can easily check the crucial, simple property that jt on an exact form is nothing but the boundary, right? F of xt minus f of x naught. That's the one of the basic properties that will define a geometric graph, the Stratonovich integral. Is everybody? So if x is smooth, this is clear. So we can make stochastic integral in such a way that this property is still true. Is everybody familiar to Stratonovich integrals? No. Okay. Okay. It's just. Okay, I think. Okay, maybe it's time is over. Yes. Okay. Okay. We will. But Ito integral, yes. Okay. Okay. Then.
Let's thank Mauro.
I'm here every day. I'm in office 311 every day. If anybody has questions, please come. I'm here every day.